Prove. Use examples to hypothesize whether the product of an odd function and an even function is even or odd. Then prove your hypothesis. First of all, let me take here one pen. We took a parent function f, which means is x squared. The parent function of a quadratic function x squared is an even function. If you look at this even function is symmetric with respect to y-axis, and we got this g function, which is a parent function of cubic functions x cubic, and this is a symmetric. The odd function is a symmetric function with respect to origin 0. So in other words, let's say f of x, let me write, because f of x is equal with x squared, and let's take here now g of x is equal with x cubic. Okay, and now we want to look their product. What's going their product to be? So f times g, let's say f times g of x. I'm taking these two examples here. In these two examples here, we already see here we have a x squared times x cubic. X squared times x cubic. This is a simple example that gives our possibility to see easier the result. If we multiply this, x squared times x cubic is x in the fifth. X in the fifth we already see is an odd function, and it's going to be similar with the x cubic function, but it's going to be a little bit wider. The graph of the function is going to be wider, little bit wider, but again it's going to be symmetric with the origin. And if you see the exponent here, the exponent is odd. In other words, always the even function, when we are changing the argument x, the argument is not going to change anything, because it's going to be f of x, so it's not going to change the sign of the function f, because as we see here, the function f is with respect to y is on the upper side, it is above 0, so it's a positive. And if we take in, for example, the g of x, if it's even, like in this case would we have even, just let me erase and let me write with a different color, maybe it's the color what is the graph. And g of minus x, if we are changing the argument here x, the sign of the argument, and odd function is going to be equal with the minus g of x. And now this is a general form how we can interpret the even function. This is an even function, let me write with the e, and this is an odd function, let me write with the o, odd function. But now we want to know the product in a general, if the product of the even function and the odd function, what is going to give. In the specific example here, we already see when we have the product of an even and odd function, we already got an odd function. But let's see in a general when can we prove it. And here in this case we have a f times g, so let me take a different colors, times g is going to be what? We have a f of x. F of x is a positive, f of x time minus g of x, minus g of x, minus g of x. And if we multiply everything here, is going to be equal with a positive times negative is a negative, f of x times g of x, f of x times g of x. times g of x. So it means is odd function, because let me take f of x and g of x, and let me write just in one as one function. Let's say is a r, is a r function, so is minus r of x. But no, f and g is equal with the r. Let's say this is r of minus x, because both of them will be multiplied when we change the argument to minus x. F of minus x and g of minus x, r of minus x, when we multiply them we get minus r of x, which which uh, uh, which can fill, or which can satisfy the condition of the odd function. It means that when we multiply odd function with even function we get odd function. So this is a proof, completes the proof.